It's a pleasure to welcome our speaker today. It's Tullio Ceccherini-Silberstein from University of Sannio in Benevento, Italy, and he's going to tell us something about a Garden of Edent theorem for Abelian Harmonic Models.
So I would like to start with thanking Paul, Ilya, everybody for the invitation to visit the University of Illinois Urbana-Champaign. It is a greater pleasure and honor to be here and to see Carl, Derek, Florine, so old friends. So the Garden of Edent theorem is an important result in symbolic dynamics, which has recently been extended following Gromov's suggestion to more general dynamical systems. So in the colloquium talk, which I will give on Thursday, I will present a more general overview of this theorem, but the title will be The Garden of Edent Theorem, Old and New. But today, I would like to report a newest result obtained in collaboration with Michel, Coornaert, and Hanfeng, which is related to some particular dynamical systems which were studied and developed especially by Klaus Schmidt and collaborators, so-called algebraic dynamical systems. I will explain what they are, but let me first start with reminding you or explaining what's the classical Garden of Edent theorem. So let me start with introducing notation. So G would be a group. A would be a finite set, which we will refer to it as the alphabet. And then you build the so-called configuration space, which is the set of all maps from G to A, which you can regard as the product of the copies of A, which you equip with topology. You give each factor A, which is a finite set, the discrete topology, and then the product topology. So this is called the pro-discrete topology, which is nothing else than the pointwise convergence. A is finite, so this will be compact by Tikhonov theorem. Okay, then we also equip it with an action of the group, the so-called G-shift. So if I have a configuration, so a map from G to A, and I have an element in the group, let me define the new configuration Gx as the one taking the value at H given by X G inverse H. Okay, this is the G-shift. You can easily check that it is continuous with respect to that topology. Okay, now I want to introduce some further notation. If I have two configurations, let me say that they are almost equal, and I will write this way. If they differ, if they differ only at finitely many points. So let me write it this way. If there exists a finite set of the group, such that if you restrict the complement of such a set, X, that it is the same as the restriction of G to the complement of F. So they agree except in the complement of a finite subset F. So they are almost equal, okay? Clearly, this is an equivalence relation which partitions your configuration space. And then I would say that the map tau from the configuration space into itself is pre-injective if the restriction of tau to each equivalence class is injective. So if you have the following, if you have two almost equal configurations and they have the same image under tau, then they must be equal, okay? So if you drop this condition, this is classical injectivity, okay? So this is a weak condition because you just require injectivity restricted to each equivalence class given by almost equality. Okay, then let me introduce the last concept. A map like here is a cellular automaton provided if it is continuous, so with respect to the discrete topology, and it is G equivariant. So equivariant, that means that it commutes with the shift. So in other words, if I have a configuration, I act with the group element G, I get the new configuration, I apply tau, so I get a new configuration here, and this is nothing but the shift by G of the image of tau. Okay? So this is G equivariance. Okay, so now the Garden of Edent theorem, which was proved for the group G equal the free abelian group by Moore and Michel in the early 60s, and it was extended to amenable groups in collaboration with Tony McKee, a good friend of Paul's, and Fabio Scarabotti, is the following. If you have tau, if A is finite, if you have tau a cellular automaton, then tau is surjective. If and only if tau is pre-injective. Okay? So, you know, in category theory, you have equivalences. For example, you can characterize a set being finite if every self-map which is surjective is injective, or vice versa. For endomorphisms of vector spaces, if it is finite dimensional, then again you have this equivalence between surjectivity and injectivity. And here in this category here, you have this kind of spaces, surjectivity is not equivalent to injectivity, but to this weaker condition. Okay, so this is the theorem. Okay, so now, as I said, Gromov suggested that such a result should be Gromov, ipse dixit, that this result should be extended to more general dynamical systems. So let me say, what will be a dynamical system? I will have X, let me write it in full as a triple. So X is a compact, metrizable space. G is a countable group. Let me write it. Now I will suppose that it is countable. Here was not necessarily. And alpha is an action which is continuous by homeomorphisms. Okay? So this clearly is a generalization of this setting. For example, a distance here, if you have two configurations, let's say that G is something like that, gamma n. Is countable, so you can have an enumeration. So it is 1 over 2n, the Dirac of x gamma n, y gamma n. So you count the point at which they differ, and you make the series convergent in this way. Okay? So for such dynamical system with some, these are Gromov's word, hyperbolic flavor. Okay, So with Michel Coornaert, we started such a program, and we tried to generalize these notions, okay? So now, if I have to, let me fix a compatible distance with the topology, then I will say that 2 points are homoclinical, and I will write X with H if I write this way. If the distance between gamma X and gamma Y tends to 0 as gamma tends to infinity in the group. So this is a standard notation for the following. For every epsilon, there exists a finite subset of G such that you have that the distance of gamma X and gamma Y is less than epsilon for all gamma in the complement of F. So if you go far away, the distance between the 2 points X and Y. So it says, you see, if you fix X and you let gamma vary, that's the orbit, okay? So that means that at infinity, the 2 orbits are very, very close, okay? They tend to 0, okay? Okay, again, this is clearly an equivalence relation. You use the property of the metric. And this, for example, if X is the configuration space defined here, then you see that 2 points are almost equal is exactly the same. It's a useful exercise to say that they are homoclinical, where the action is clearly the shift. Okay? Okay, so this is the generalization of this notion. Well, the other notion, preinjectivity, I would say that the map tau from X to X is preinjective exactly in the same way. So if it is injective when restricted to each homoclinicity class, okay? And then I will say that a self-map of X and X is an endomorphism. I should say an endomorphism of the dynamical system if, exactly as before, it is continuous and G equivariant. So just by definition, in the previous case, the endomorphisms are exactly the cellular automata, right? Because that was my definition, okay? Okay, so now our purpose is to state an analogous theorem in this setting. But for this, I first want to introduce you a class of dynamical system, the so-called algebraic dynamical system. And we do it in the following way. So G is again a group. Let me denote by, in this way, the so-called group ring. So it's the set of formal expression in this way, where the sum is finite. So the coefficients are in Z, and they are different from 0 except for finitely many group elements, okay? It's well known that it is a ring. It's called the group ring of the group with coefficients in Z, okay? Now, if I take an element, such an element F, then I denote by MF the quotient of the ring by the principal left ideal generated by F. So it would be ZGF. Okay, so this is a ZG model. So in particular, it is an abelian countable group with respect to addition. And therefore, I will give some details explained by Pontryagin duality. You can associate with it something which I called XF, which is the Pontryagin dual, Pontryagin duality theory. And the dual action, you see, I said it's a ZG module. So in particular, G acts on this abelian group, and the dual action will give you an action of the group on this space. This is a compact metrizable space, and G acts on XF in a dual way. I will explain this later. So we have a dynamical system, and this dynamical system is called an algebraic dynamical system. Okay? This. Excuse me?
What's the third item in this triple?
Alpha F is the action, is the dual action. Yes, you're right, dual action. Okay, so let me give you a couple of examples. Okay, maybe later. Okay, let me go to now define the class of algebraic dynamical systems for which the theorem applies. Okay, let me say that F is weakly expansive. Let me write just like that. Weakly expansive if the following two conditions are met. The map G goes to Fg with G in C0 of G. So this is the real vector space of all functions defined on real function tending to 0 at infinity, C0, okay? And Fg, this is the convolution product. So what is Fg at gamma is the sum F delta G delta inverse gamma over the group is injective. In fact, C0G is, in this case, it's a left ZG module. It means just that it is a torsion-free module, okay? This is the first condition. The second condition is that F has a right inverse with respect to this action in C0G. So there exists omega in C0G such that F omega is equal to the Dirac delta at the identity element of the group. Okay, so this are the conditions defining such a weakly expansive element. And then the theorem is the following. Suppose that G is abelian. Suppose that F is weakly expansive, that the phase space XF is connected. Then, if I have a map which is an endomorphism, then it is surjective if and only if it is preinjective. Okay, so we have the analogous statement. So why is this notion weak expansive interesting? Because if we remove weakness, you have the notion of expansive, which is a well-known notion in the theory of dynamical systems. So if you have a dynamical system, is called, this is a new notion. This is classical, expansive. If the following holds, so let me fix a distance which is compatible with the metric. So there exists a positive constant, it's called an expansive constant, such that if you have two distinct points in X, there exists an element in the group such that the distance make them slightly far away. So they can be very, very close, but then moving them via the group, you can at least separate them by this universal constant delta, which clearly depends on D, but the definition is independent of the distance because X is compact. Okay, so this is a notion. So now, let me give you a couple of examples. For example, all the shifts that I have defined there, so I have a power g with a finite. And group G, and the alpha is the shift. This is expansive. Another interesting example is provided from the following situation. So let me take, for simplicity, just the two-dimensional torus, which is just, okay? And let A be a 2x2 invertible matrix with z with coefficient in z, but whose inverse also is in z. So I will write GL to z. Okay, so it has determinant plus or minus 1, so it's invertible. Okay, then A induces an homeomorphism of, okay, let me use the same notation. I can write it this way, okay? In the obvious way, okay? I take x, y. Everything is defined modulo z squared, but it's clear that what it means, okay? So this is called a toral automorphism. And this map, if you consider the iterations of this map, then you get a dynamical system. You apply n times or minus m times. In the sense, you take the inverse. So you have an action. Now the group is Z. And the action, let me write A that way. And this is the dynamical system. And it is expansive if and only if there are no eigenvalues of this matrix of absolute value 1. Okay? So this is the same thing. Actually, I'm saying that the matrix A is hyperbolic, and this groups geometry, and let's say something about geometry, so it yields as an anodes of diffeomorphism. So this is a manifold, so it yields an anodes of diffeomorphism. I don't go further in the details because otherwise we waste too much time. And the classical example is Arnold cat map, which is, let me write R with A, Arnold. And in this case, the two eigenvalues are 1 plus square root of 5 plus or minus square root of 5. So the positive one is the golden mean. Okay? I will return to this later. So we have a remark. Is it okay to write here? It's a remark that weakly expansive implies expansive. Okay? So as a corollary of our...
So the other way around? This way.
Yeah, you're right. Yes, thank you very much. So as a corollary, if instead of weakly expansive, we can replace expansivity and have such a result. Okay? But so this story, no, this happens in life. So with Michel, we first proved it for expansive actions. And shortly after, Hanfeng generalized this result to more general setting, not just algebraic actions, for expansive actions. And so eventually, I found a paper with Hanfeng and Louis Bowen where they were treating, I will discuss now, these harmonic models, and I understood that the key point would work in a more general setting. And so I contacted Hanfeng, and we discussed this together, and we realized that, in fact, the proof works in this more general setting with this, where is it? With these suitable definitions, and this is the point. Okay, so now the last term I want to introduce you are the harmonic models. So I start again with an element in the group ring, and I say that it is well balanced if it satisfies the following conditions. So well balanced one is that the sum of all the coefficients is equal to 0. Second condition is that all the coefficients are negative except clearly one. So for all gamma in G except the identity element. Third condition, it is self-adjoint. So if I look at the coefficient at gamma and at its inverse, they are the same. So this is the notion of self-adjointness. And the fourth condition is that the support of F, which clearly is the set of group elements at which the coefficients do not vanish, generates the group G. Okay, so that you have sort of irreducibility of this action. Okay? Okay, so for example, if I take G equal to Z squared, so in this case, the group ring would just be D, more general. In this case, the group ring are nothing but the Laurent polynomial in D commuting variables, okay? So ZG, I will write it as U1 plus or minus 1, UD plus or minus 1, okay? The Laurent polynomials, okay? And for example, I can take F to be 2D minus, well, let's write this way, UI plus UI inverse, okay? So this should remind you of the Laplace equation, and we will find it later, okay? So this is why this kind of, the associated dynamical system are called harmonic models. Okay? Just because this basic fundamental example is Laplace equation, and the solutions are the harmonic functions. Okay? Now, what's the relation between harmonic models and the previous stuff is the following. We prove this, let's call it a remark. Suppose that G is not virtually Z or z square, then well-balanced implies weakly expansive. So again, in this theorem here, if I have G abelian and F is abelian but not virtually Z or Z square, for example, Z3 and so on. If F is well balanced, the phase space is connected, then you have the Garden of Edent theorem, the equivalence between surjectivity and projectivity of every endomorphism. Okay?
So in this remark, does G have to be abelian or not?
No. No, no, no. Okay, so I have presented the statements. Now I would like to give you some ideas which are related to these constructions and try to make more links between the examples that I've written down. Okay, so let me start first with just reviewing some basic of Pontryagin theory. So what X now is a locally compact abelian group. So locally compact means that the identity element has compact neighborhoods, okay? And is Hausdorff. It's implicit that it is also Hausdorff, okay? Then a continuous group homomorphism from X to the torus, to the unit circle group, is called the character. And the set of characters is called the dual group of X. If you equip it with the with pointwise multiplication, so the product of two characters is a pointwise multiplication of the functions, and you look at convergence on uniform convergence on compact subsets, then this also becomes a locally compact abelian group, which is called the Pontryagin dual of X. Okay? Okay, as an example, what if I take ZD, the free abelian group, then its dual, well, I can write this thing. Its dual is the d-dimensional torus. Okay? If I take the d-dimensional torus and I take its dual, I get back to ZD. If I take RD, R is the real, as a local compact abelian group, then its dual is, well, I should say isomorphic to be more precise, okay? To the group itself, okay? So there is something going on. In fact, there is a theorem, this is Pontryagin duality. If you look at the map from X into the dual of the dual, so if you have X, you associate iota X, which is as you do for vector spaces, you know, the bidual of the vector space is canonical isomorphic. This is as a homeomorphism, and homeo and also group homomorphism. This group So you can say it is a locally compact abelian group isomorphism. So it preserves the topology, the group structure, and everything, okay? And this is so-called Pontryagin duality. Okay. Now there is a sort of dictionary. So if X is compact, then this is equivalent to its dual being discrete. So if X is discrete, its dual is compact. Metrizable is equivalent to the dual being sigma compact. So if you have compact plus metrizable, it's the same thing as discrete, as its dual being discrete and countable. At last, let me say, if it is compact, I have a characterization of being connected, which I need here because it's part of the hypothesis. This is the same thing. Okay, here I have discrete. That this is torsion-free. So there are no non-trivial elements of finite order. Torsion-free. Okay. Let me just add the following. The last notion I need. Suppose I have, so in our setting, what we are more interested is X compact, so the dual will be discrete. So this was exactly the situation which I described here. This is discrete, and its dual will be compact indeed. This is G was by hypothesis countable, so this is countable, so its dual will be metrizable. Okay? This explains. Now, suppose I have, let me suppose now that X is compact. It's not necessarily actual, but okay. So this is a closed subgroup. Then I can consider the quotient group X over Y, and I can take its dual. Then this is isomorphic to the so-called annihilator of Y, which is just the set of all characters of X, the dual, such that they vanish on the elements of Y. It is something classical, huh? For all Y and Y. Okay? This is called so this, let me repeat. I have to. So this will be a subgroup of the dual. Okay? In fact, this kind of construction yields bijective correspondence between the quotients of the locally compact group X and subgroups of the locally compact dual X hat. Okay? Okay, so now there is still one last notion. Suppose I have lambda, which is continuous group homomorphism between two locally compact abelian groups. So continuous group homomorphism. Okay? Then I have if this induces by duality a map which I denote by lambda hat from the dual of Y to the dual of X in the usual way. How you do it? You compose of a character is just Okay? So lambda brings an element of x into y. You apply the character of y, and you get an element in the torus, and this is it. Okay? And then you have a little dictionary that if lambda is surjective, then lambda hat is injective. Vice versa, if lambda is injective, then its dual is has dense image. In general, it's not surjective. However, if x and y are both either compact, so both compact, or both discrete, you have the lambda is surjective injective if and only if lambda hat is injective surjective. Okay, so they switched. Okay, this is exactly our setting because we are looking at compact compact spaces, and their duals, which are these rings, are discrete. So we can really make all use of this equivalence. Okay. So now I want you to better understand what is this XF. So what is this? Okay? XF. So let me use this characterization here. If I taking X to be ZG, Y is subgroup. I regard it not just as a subring or as an ideal, just as a subgroup. Then, what is XF? Which by definition is the dual of the quotient. So this should be the annihilator of Y. So this is the annihilator of Z, G, F, right? Okay, now I erase here the annihilator between us. What is X hat? ZG. So this is a direct sum of copies of Z, because okay. So when you take dual, you have the dual of Z is the torus. But now you have infinite products. So I write it this way. All possible sequences indexed by G. Okay? So what will this be? So will be the elements there. So remember the notation I used at the very beginning. So these are all the mass from G to T, such that the sum F gamma X delta gamma is equal to 0 for every delta in the group. Okay? So if you take this is just the element, because I need to ask for all the ring, not just for this element here. This with just delta, this means that it's orthogonal to F. But then I have all the action of G. By linearity, I only need to have this translate by delta. Okay? So let us think of what let me do with this example here. So example, let me take the following. G is equal to Z, and I take F to be 1 plus U minus U squared, okay? As I said, the group ring are the Laurent polynomial in one single variable. So I write it that way. So what does this condition give? So in this case, what is xf? So these are the elements. So the bi-infinite sequences, such that xn plus xn plus 1 minus xn plus 2 is equal to 0. I can write it this way. It's equal to xn plus 2, everything clearly mod 1, for every n in Z. Okay? So this, the role of delta is played by n here because it's the same group. Okay? So you see, you have this local condition which shifts. This, in fact, is a closed subshift. Now I want to show you something very exciting, I guess. We have xf here. Here I have the shift, because this is a subshift of t power z. So I have the shift. Now let me apply I define something on the two torus. If I have an element x, I map it to the pair x evaluated at 0 and x evaluated at 1. I claim that this is bijective. Why? You see, if I know the 0 and 1 coordinate, then I know the position at 2, because it's just the sum of the two. If I know this and this, and backwards. So this is really bijective. It's continuous. It's a homomorphism. And now let's see what happens if I do the shift. If I go the shift, this element here goes, let's say, the shifted sigma. I don't know, right? This will be the pair x1, x2. Do you agree? I shift, okay? But now, what is it? What is x1 is the second coordinate, and x2 is just the sum of the previous two. So this is nothing but I apply Arnold map here to, right? Because you get x1 here, and then the sum of the two, but the sum of the two is exactly the same. Okay? So this dynamical system here, this algebraic dynamical system, is the same thing as this toral automorphisms given by Arnold's cat. Okay? So this is just to explain how things are related. Okay? Okay. 1 minute left. I wanted to say something about the proof very quickly. Let me write it here very, very quickly. So what does the proof consist of? There are two main ingredients. So first, let me define by delta x alpha the so-called homoclinic group. So what is this? Is the set of the element of the X, the Abelian group, such that they are homoclinic to 0, the 0 element of the group. Okay, it's easy to see that it is a group, and our theorem, the key point is that delta is dense in X. So delta F is dense when F is weakly expansive. And moreover, delta F is isomorphic to this module here. Okay, I should write F star, the adjoint. Anyway, so this is as ZG module. Okay, so this is a very important thing. So in the case of the Arnold-Ket map, you know, you have the two eigen directions. One is expanding, the other is contracting, okay? And they wrap around the torus in orthogonal way, and the point of intersections are exactly the point of the homoclinic group, okay? And in fact, they are dense. This is well known from the theory of annals of diffeomorphism, but this is a generalization in this setting. First theorem. And then the second theorem is a rigidity, which means that if F is weakly expansive, then any tau endo of the dynamical system is affine. So affine means that tau of x is of this form, where lambda is a continuous group homomorphism, and T in X is a translational part. So this is translation. So again, this rigidity result is a generalization of classical result by Walters for annals of diffeomorphism, toral automorphism. But this rigidity result plays a fundamental role, because now, because of this map being surjective, you know, when you translate it doesn't matter, you want lambda to be surjective. But now surjectivity of lambda is equivalent to lambda hat being injective. Then you use this property here, that they are isomorphic. So when you restrict it to the homoclinic group, you indeed get preinjectivity, because preinjectivity means that it is injective when restricted to each homoclinicity class, okay? And the homoclinicity class are nothing but the cosets of this subgroup here, okay? So I hope I could give you at least a quick idea of the proof. Thank you very much for your attention.